Today we are going to see cantilever slab. We have this problem, that is design a cantilever slab. Effective span is given. So as effective span is given, we need not require to go for center to center distance or clear span plus effective depth. This value we have to take as it is. Floor finish is given 1.25, live load is given 3.25, M20, and here keep in mind Fe 250. So KU max we have 0.53. We should be very careful with this. Otherwise we are habitual with 0.48 or 0.46. So draw details of reinforcement. So effective span L effective 1.2 meter. The step 1 we have this one. Step 2 trial depth. Now L effective upon 7 into modification factor, and we know we have these values, that is 7, that is given on page number 38. So if we will go to page number 38, clause number 23.2.1. So we should know in examination expected, you can write it clause number 23.2.1. And modification factor we have to take, that is from figure 4. So we have modification factor from figure 4. And we are assuming modification factor 1.4, assuming percentage of steel 0.4%. And then we are going to get from this value of D, that is L effective is 1200 upon D is equal to 7 into 1.4. This value you can someone go 1.3, someone go 1.45. So that you have to assume. And then we have from this D, we will get it as 122.45 millimeters. Now generally in the slabs, we are going to take this effective cover D dash, that is equal to 20 millimeters. So we have D equal to, so this is D plus 20. So I can write it as D plus D dash. And then from this we will get 122.45, which we have calculated over here, plus 20, which will be D dash value, that will gives me 142.45 millimeter. Now we will provide overall depth, that is 150 millimeters. And then we will get small d we have D minus D dash, and that we will get 150 minus 20, and value we are going to get as 130 millimeters. Then once we have this value, then we will go to step 3, which is load calculations. And in this we have total load, that is dead load plus live load. Now we know dead load we have, that is self weight of slab plus floor finish. So we have these two values. Now self weight of slab 25 into D. Overall depth we have, that is 150 millimeters. So 25 into 0.15, that will gives me value 3.75 kilonewton per meter square. Now floor finish is given 1.25. So if we will add these two, then we will get total dead load, that will be equal to 5 kilonewton per meter square. So now knowing this total dead load, we have to add in this live load, which is given as 3.25 kilonewton per meter. Floor finish is also given, live load is also given. If not given, we have to assume these values. Then we have total load, that is dead load plus live load. So we have 5 plus 3.25, that will be 8.25 kilonewton per meter square. Once go through the calculations also, then we will go factor total factor load. So we can have 1.5 into 8.25, which will gives me 12.38 kilonewton per meter square. So this will be my third step, which is load calculations. Then we will go with shear force and bending moment calculations. So we are not going to check actually for shear force, but steps if we will see in slabs, we are in this fashion. Then a beam is cantilever, therefore we have reaction that is equal to total load. So 12.38 into 1.2, that is 14.86 kilonewton. Then we have bending moment WU L effective square by 2, and then W we have WU. So this is also WU. So 12.38 into 1.2 square by 2, that is 8.91 kilonewton meter. If you will not go for this step, that is shear force, you can directly go to bending moment calculations also. In slabs, actually, this step is not required. So you can go step 4 bending moment calculation, and directly you can have bending moment WU L effective square by 2, because we have slab as cantilever. So you can mention cantilever slab, and then you can write WU is equal to, sorry, cantilever slab, and then you can write MU is equal to WUL effective square by 2. So this actually we have, that is ultimate moment on 8.91 kilonewton meter. So now knowing value of mu, we can check depth from bending moment consideration. So here we should be very careful. We have to take Ku max as 0.53. Then we know value of Ku max 0.53. So we will find Ru max. And we have Ru max that is 0.36 FCK. We have 20. Then Ku max 0.531 minus 0.42. Ku max again 0.53. So we will get this value 2.97 Newton per mm square. Then knowing this value, we can find value of D required. So we know mu max, we know Ru max. B is taken as 1000. So we will get this value 8.91 into 10 raised to 6. And from this, we will get value of D, that is 54.77 millimeter. So now you have to keep in mind. So we have this WU 12.38. So if we will go back, so here we have 12.38 kilonewton per meter square. Actually, you have to go one step over here, that assume unit width. Assume unit width of slab. Unit width of slab. So this is actually important, and therefore we have WU is equal to 12.38 kilonewton per meter. That actually you have to add over there. Then we have this value. So we know now D 54.77 millimeter, and this is 130 millimeter. This is D provided. So we have D provided greater than D required. Therefore, okay. Then we have reinforcement. So we have main reinforcement. AST equal to 0.5 FCK upon FY 1 minus root of 1 minus 4.6 MU upon FCK BD square into BD. B we have to take 1000 millimeters, so we have substituted 0.5 FCK 20 FY we have 250. Be careful with this. 1 minus 4.6 8.91 and all these values. This is 1000. This is small d, and we have this value. And this will gives me value of AST 325.46 millimeter square. And then AST minimum we have 0.12% of BD, and then we will substitute this 0.12 into B we have 1000, D we have 150, and from this we will get 180 mm square, and this value is less than 325.46. So we have to provide this value. If this value comes less, then we have to go AST minimum. Then spacing of reinforcement. So we will use 8 mm diameter because we have area less, or you can go for 10 also. That does not have any problem. So we have this overall depth. Now in this we have overall depth that is 150, and then we have 150 upon 8, and that value we will get it as 150 by 8, that is 18.75. So we have this value actually 18.75 millimeters. So we can take bar up to 16 millimeters, but generally in slabs we will go for 8 or 10 millimeters only. Then we have spacing. So we will get this spacing that is 154.46 millimeter. We have to always provide less than this. So area provided will be greater than this one. And then this value will be less than 300 mm and 3D, because 3D we have 130. So 130 into 3, this comes 390 mm, and this is less than this. Then we have provided 8 mm diameter bars at 150 mm center to center, and this will be my main reinforcement as main reinforcement. And then we will go with distribution reinforcement, and then we have to calculate AST provided, and we have AST provided, that is here we are going to keep spacing. Just we have taken spacing here and AST over here, and this will gives me AST provided is greater than AST required. This is AST required value, so this is okay. Now we will go to the distribution reinforcement, and we have to provide it as minimum reinforcement, which is 180 mm square, and just calculate 8 mm diameter bars, and spacing we will get it as 279.25 millimeter, provided 8 mm as 270. Now as we have this as cantilever beam, so we have tension at top. So we have 8 mm at 150 mm center to center. So this is my main reinforcement, and 8 mm at 270 mm center to center. This is my distributed reinforcement. And this section actually we have to distribution steel. So this diagram we have to plot, and distribution steel is always inside of Main reinforcement we have always, that is on outer side. So this is this problem that is related with your cantilever slab. So this is our revision lecture number 4. So now we will stop here only. Thank you.